always have to sit in the back.
Yes, sir.
Yeah, you know. He's auditing the course. So I think it's time. I don't know the. Okay, so we're going to do these chapter 8 problems, right?
Yes.
Real quickly. Remember the bosun's chair?
Yes.
Interesting thing. It should have be gotten somehow into this chapter. I'm going to work on that. But remember, somebody. I don't think we have the time. But remember, somebody pulling this person in the chair up has to exert a certain force to get this person to lift the person off the ground, right? So if you exert slightly greater force, then the person's going to rise through some distance. And you got to do work to do that. In fact, we know how much work it is now. It's mgh, right? Because what you're doing is you're balancing gravity. You're exerting a force through a distance, and the distance you pull here is going to be the distance the person rises. This is the person standing off to the side, right? But what about the person in the bosun's chair? Suppose that person exerts just enough force to lift the chair and goes through the same distance. Well, it's half the force. So what has to be the case for the person sitting in the chair pulling? You go through some height h. The person has to do work, mgh. But the person's exerting a force of half mg. So what has to be true?
He's going half his.
No, but we're constructed the same distance. That's a constraint we're putting on the problem.
Pulleys do? No. The tension?
Where does the energy come from?
The pulley?
Oh, come on. It's not what do you think, there's like a motor in the pulley or something? The pulley's passive. It's nothing. No, the person has to pull through twice the distance. Yeah, and if you think about it, you got to think about it. That's the only way out of this paradox. You're not going to violate energy conservation. So people lifting, an engine block. We talked about that. If you've ever done it, or if you've seen them, what they're doing, it's like this, and the engine block is very slowly moving. So they're doing the same amount of work. They're doing mgh, but the force they're exerting is much less. They wouldn't be able to exert a direct force and do it. Wouldn't be able to exert that amount of force, but they're exerting less force. The price they pay is it's through a much bigger distance, and that needs to be. That was done early on in Newton's stuff. It needs to be gotten into the energy things here somewhere, somehow. So I'm going to work on that. But I wanted to tell you. Okay. So conceptual questions. Let's see. Question number 2. So here's the diagram. We got this mass gravitational field. There's this smooth ramp here, and there are these hills here. They all have the same radius of curvature. You'll see why that's important in a minute here. And there's no friction, and it's released from rest. So what's the first one? We're given the dimensions here. Whoops, I'm looking at the wrong. Oh, God, they got this diagram that you want to look at that's not the right, it's the one below. Okay. The block is released from rest. It remains in contact with this ramp thing here, or whatever you want to call it. Okay. Which eventually, what's going to happen here? It's going to be released. It's going to slide down here. It goes over here. What's eventually going to happen? It speeds up here. It slows down. Speeds up. Slows down, more. Eventually, is it going to make it past this hill? No. And the reason is that it's got this this curve here. You can think of as the potential energy, because the potential energy is excuse me. I think we called it U in this class mg. The gravitational potential energy is mgy, and you can measure from anywhere. You can measure from down here if you like. if you want to. Doesn't matter. Just stick with it, any reference location. So this curve here is proportional. This is y. So this curve is proportional to the potential energy. And we've got an amount of energy here. There's some initial energy, which is mg. I can call this h here. Oh, sorry, can everybody see that? Okay, so we've got this initial energy, mgh. So this is somewhat like the potential energies. Remember we did this, we talked about yesterday about the potential energy curves? However, this is not that was actually one-dimensional, and we'll do an example later. This is a two-dimensional problem, but it's the same idea. This thing's going to pick up speed here. Gravitational potential energy goes into kinetic energy, and then it comes back. Eventually, it's going to turn around at this point. It's got to turn around. At this point, it can have no kinetic energy because it's back to its original energy, which was all potential energy. So it's going to turn around, and then what's it going to do? It's going to momentarily stop here. Then what does it do?
Goes back to that.
And then what does it do?
It'll go back to the first.
And then what does it do? Yeah, this is an oscillator, a complicated oscillator, but it's just going to go, in the absence of friction, it's just going to go back and forth between these two turning points here. What does the block do after failing to, okay. On which hilltop is the centripetal acceleration of the block the greatest? So it's moving in the path of a circle up here. We have approximately uniform circular motion along a little distance here, as we've discussed before. And the centripetal acceleration is v squared over r, where r is the radius of curvature, right? They all have the same radius of curvature. We're told that. So therefore, the greatest acceleration is going to be the hill that has the greatest speed. And which one's that? Number one. That's right. Because we have the smallest potential energy. So we're going to have the greatest kinetic energy for the hilltops here. Among these possibilities right here, the kinetic energy is going to be greatest here because it has the least potential energy. So the answer is 1. What about the normal force? We're asked, I think, which hill has the minimum normal force? Well, we have a force diagram for the top of the hills here. We've got, I'm going to choose down to be positive here. There's a gravitational force, and there's a normal force pointing in the opposite direction at each one of these points here. And that has to be mv squared over r. So to get the minimum n, you want the biggest v. You want the biggest speed. And that's going to again be this hill. So the normal force will be less here. You know, another way physically of looking at it is this thing could fly off. We're told it doesn't fly off the hill, right? We're told that. But if there's going to be a hill what's the easiest hill for it to fly off on? It's this one. And the moment it flies off, the normal force goes to 0. So it's just looking at it slightly different point of view. Okay, any questions about that? So number 3, we have this block moving here, and there's these 3 different paths. And we're in a gravitational field. See, is this? Yeah, I think this is the problem. And then this is the finish line there. God. Okay. So it can take these 3 different routes. And this is frictionless. Ranks the routes according to the speed of the block at the finish line. So which of these 3 paths is the block going to be moving the fast at the finish line? Yeah, it's going to be this one because it's going to pick up speed. You can think of it dynamically from a Newtonian point of view. Gravity is going to accelerate it here, right? So this is going to get first, second, and third. From an energy point of view, losing gravitational potential energy, it's going to go into the kinetic energy. So it will have the greatest kinetic energy down. So it's going to be moving faster. So you can look at it either way. They're equivalent. What about the time? Which one's going to get there first? Or do they all get there at the same time? It's pretty obvious, right? This one picks up speed. Yeah, this one it's going to be the same one. It's sorry. What? Oh, so the time, right? This is going to be the shortest time, right? So the greatest time is going to be the top one. Okay. All right. Any questions about that? Trick question. Okay, one more of the conceptual type questions. This is a diagram. This is diagram 829. So we have this, again, a block, and moving along this curved ramp, and part of it is, I think it starts, so it goes like this, goes down like this, and then goes, is it like this? This would make sense, yeah. So this is rough here. So here we have friction. Gosh. Remember I told you about the Chinese chalk? Okay, well, we got French chalk now. This is not a joke. And this is true. It crumbles really easily. I'm not going to say any more about that. Like, I'm not kidding you.
Any pressure applied, they crumble.
Yeah, I'm not kidding you. This is true. You can come up here after class. Okay, so this is supposed to be, this is rough. We got friction here, right? This thing starts up here. Okay, and it slides from A to C along. Frictionless horizontal frictional section. Is the block's kinetic energy increasing, decreasing, or constant from here to here, from A to B? I guess this is C at the beginning of the, yeah. Okay. And I guess it comes to rest here. Yeah. So what's the answer to the first part? The kinetic energy is going to be conserved. Mechanical energy is conserved here. It's not conserved here. Mechanical energy is not conserved. We're losing mechanical energy into heat. Okay? But the first part, for this part, this energy is conserved. The gravitational potential energy here is decreasing. We're getting lower in the gravitational field. That energy is going into kinetic energy. Right? So from A to B, the kinetic energy will be increasing because, this should really be because U is decreasing. What about from B to C? That's the opposite, right? Now the kinetic energy is maximum is down here. It's going to be decreasing because U is increasing. And now, what's happening to the kinetic energy along the frictional section? It's decreasing. The potential energy is constant. So we're losing mechanical energy. It's going into heat due to the friction. Yeah, I think that's it. Any questions about that one? Okay, so the loop. There's a lot of variations on the loop problem, right? It's an old standard problem here. So in this one, we've got a block, starts up here, frictionless track. I don't like this P. R is the radius, and they're calling the points P and Q, so I'm relabeling. And we're going to call this point 1 and point 2. And this is the initial point. Okay, I don't like this PQ and PQ and R. Yeah, I don't like that. Okay, so we're told the mass. It's released from rest at this point up here. Okay. Oh yeah, we're given these values, and we're asked here, how much work does the gravitational force do on the block as the block travels from the initial point to the second and to the third point? So what's the work done by gravity? Remember, the work done by gravity is choosing up to be positive. It's mg times the change in height, which is the final height minus the initial height. And in this problem, it's better, I think. Like we have the work done by gravity is minus mg delta y. Y is the final value minus the initial value, right? So, and this is h. So, so this is easier to get rid of this, to not deal with these signs. Okay, this puts it in, everything's going to be, this is going to be positive because our final value is always going to be less than h. So it's easier. That's what I did here. I should have written it in here. So the work done by gravity from here to point 1 is just mg times the initial height minus the final height. The final height is r. So we know all this, we can calculate it, it's 0.15 joules. How about to this point here? What's the work done by gravity? Well, the change is going to be less because the change in height, the change in y coordinate here, change in height is less. And now instead of minus r, it's going to be 2r because this distance is 2r. We're going to choose this to be our, well, it doesn't matter. We're just doing the delta y here. But I think later on, yeah, we're going to choose that. Okay. So we can calculate this. It's 0.11 joules. Okay, for part C, what is the potential energy when the block is... Okay, well we need to, if we're going to talk about potential energy, we need a reference location. And do they tell us what to choose, or I've forgotten? Oh, yep, they're telling us here. They're saying we're going to call this zero potential energy. You don't have to. You can call that zero potential energy if you want to. All that's important are changes in the potential energy. So you just pick a reference point, we're going to pick it here, and just stick with it. So now instead of talking about changes of potential energy, we can actually talk about the potential energy at a point. That's easier to deal with. This depends upon 2 points here. So, but we can now just talk about it at a point. So the gravitational potential energy is just mgy in a uniform field, and the initial potential energy is going to be mgh. We're told what h is, so it's 0.19 joules. The gravitational potential energy at the point 1 is going to be mg times this height here, which is just mgr, so it's less, it's 0.038 joules. And here, it's going to be twice this, right? Because it's twice this high, it's going to be twice this value. There's some little bit of round off going on here, don't worry about it. And then there's an F. I forgot to write the F here. You might want to put that in. This is part F. Suppose, now this is kind of interesting. We're told that this is initially at rest. For any of these questions, is that relevant? Does this come into play? No, this is all related to gravity here, to the potential energy, the work done by gravity. It's independent of the motion here. It doesn't matter. So if you gave it some push down or even up, assuming it stays on the track, these questions, none of the answers change. Yeah?
If you give it a push up the track, it would change H, right? So wouldn't that affect you first?
See, I wouldn't say that H is something that's given to us. You can imagine doing an experiment and you measure H, right? So we're given H. That's the initial height from the ground here, right? And now you can imagine pushing it up or down. How's that going to change? So what was your question?
So my question is that you're taking the mass, H is being taken from where the mass is right at that moment.
Yeah.
But if you push the mass up further, then H changes as well. And H change
Okay.
is going to affect your...
We have initial conditions here, right? The initial conditions are the mass is at this height H here. And it can have some initial velocity. Up or down, or zero. That's the idea. Yep. So that H is a parameter, it's a constant, and and you want to think of it as an initial condition, along with a velocity. And then the basic idea in mechanics, and it's true for probably all physics, is, how's the system going to evolve for those initial conditions? That's sort of our basic goal. Given a physical system in some initial situation, how does it evolve in time? Okay, any other questions? Now, the next one is 27. And if you do what they ask you, go through this multitude of steps here. I think this problem is better looked at from an energy conservation point of view. We don't want to go through and find all these works and all that. We're just going to use energy conservation. So that's why I told you that we're just going to do A and D. So we're going to do this just from an energy conservation point of view. And here's what we're given. We've got this stone, we know its mass, it's heavy, 8 kilograms. It's resting on a spring. This is a compression spring, okay? So it's, we talked about that, right? Extension springs, the turns touch. We saw that in the uniform circular motion lab. Those were actually extension springs. So in its relaxed, what you might think is its relaxed state, you see all these turns touching. It's actually under tension in its relaxed state. And you know that because if you exert a little force, you don't move it. You have to exert a finite force in order to separate those turns. It's an extension spring. It's meant to be extended, okay? You try to compress it, it's like compressing steel or whatever, it's going to have a very high spring constant. Well, this is the opposite. This is a compression spring, okay? In equilibrium, the turns don't touch, and they're not close, okay? So it allows you to, it can handle some compression before the turns touch. So we don't know the spring constant. We're given, however, we know the mass, and we know that in equilibrium, from the unstretched state, the spring compresses by 10 centimeters. So what information can we get from that? What do you think? I think we actually talked about it. You can get the spring constant, right? Hooke's law, which governs the spring here, as long as the turns don't touch, or as long as you don't overstretch the spring, the force is going to be proportional to the displacement from equilibrium. And that proportionality constant is the spring constant. So we can draw a force diagram here. In equilibrium, I know there's gravitational force. And now, by Hooke's law, I know that there's going to be an upward force. The spring is compressed. The force is going to be up. And it's going to be the spring constant times the displacement from equilibrium. So these two things equal each other. We know everything here except K, so we can find K. And we get 784 newtons per meter. So that's the first part here. All right? And we did something similar in lecture, I think. So now we're just going to jump to the end, okay, and not go through all these gymnastics they want you to do here. And here's the bottom line. Here's what's happening. The spring is compressed 10 centimeters here. It's then compressed. Somebody comes in here and compresses it 20 more centimeters. Excuse me, 30 more centimeters. So it's compressed 10 here when you set it on there. It's compressed 10. And then somebody pushes it down 30 more centimeters. So that's a total distance of 40 centimeters from here, from the unstretched state. Right? And then it's released from rest. So we have our initial conditions here. It's a release from rest. We know how much this spring has been compressed. And once this is released from rest, this force is, by Hooke's law, this force is going to be greater. It's going to push the mass up. And the mass is going to reach some maximum height. And that's what we're after here. And we're going to measure it from, I think, we're told to measure it from this point. From the maximum, from the compressed height. We want to know the height it goes from there. That's what we're asked. So we might as well choose that to be our origin, our y origin, just to make life easier. You don't have to, but makes things easier. Okay, so everybody get what's going on here? See, this is interesting enough without having to go through all the junk that they say. I think this is getting to the point here. Okay, is energy conserved? Is mechanical energy conserved? Yeah. So very good approximation here. You would think so, but we're going to assume it. Okay, so the initial energy is going to equal the final energy. This is our initial point, right after it's, or just before it's released, or whatever. What are we going to choose as the final state here? We're going to choose the final state to be its maximum height. So the initial energy has to equal the final energy. And all along the way here, the mechanical energy will be constant. But we don't care. I mean, all we care about is the fact that the mechanical energy is constant. So therefore, the initial value is going to equal the final value. And we can call the initial and final anything we want, whatever's appropriate. So what's the initial energy? Well, there's potential energy in a spring. And that's 1/2 k times the distance compressed from equilibrium. So that's got to be 40, that's this capital D, it's 40 centimeters. So that's the initial energy, and we can calculate that. What's the initial Y value, the initial gravitational potential energy? It's 0 by our choice of reference level. Potential energy is not defined in classical mechanics. You cannot uniquely determine potential energy. Only changes in potential energy are relevant. So it depends upon your choice of reference. There's nothing wrong with that. So in this case, the initial potential energy is, for our choice here of reference, it's going to be 0. So this is the initial energy. We can calculate this. This is 0. I get 62.7 joules. The final energy, the mass will be momentarily at rest. So there's no kinetic energy. It's all potential, and that's going to be mg times the height, some height from here, up here somewhere. And we don't know what that is. Okay, I'll plug, here we go. So I put this into the revised notes. It was 1999, and it wasn't a Mars rover. It was, we talked about this, and it didn't crash, it burnt up in the Mars atmosphere. And it was a unit error. So somebody had written something like this. Right? We encountered this yesterday, remember? Yes. Now this is only true if h is in meters. So somebody had done that, and then somebody had probably put a computer code or something, and they assumed it was in so this has to be in meters. They mixed English, like feet or yards or miles or whatever. That was the mistake. So you guys, so this was some time ago. Like 16 years ago, but it's in Wikipedia. That's where I went, right? And of course, I only had a few seconds because I'm so busy, right? I didn't read it, but you can read it. Maybe you have more time than I do. I don't know. Nobody seems to have a lot of time around here. But yeah, that's interesting. So physics teachers just jumped on that. I remember announcing it in class, you need to be careful with units, right? So I'm going to write this in here. I should have done it. So I made the mistake right here. H must, when you write something like this, which engineers love to do, physicists usually don't do it, but I did it there. H has to be in meters. Otherwise, it's not true. So now we have just one equation and one unknown. The final conservation of mechanical energy tells us the initial value has to equal the final value. We can determine H. So it goes up 80 centimeters. Oh, so I guess it's twice. If this is 40 centimeters, so it's going up twice. That's where it turns around. This is a good problem because there's two forms of, you notice there's two types of potential energy here. It's mixed. It's a little bit more interesting than some of the typical problems. Potential energy can reside in two sources, the gravitational and the spring. But when you use energy conservation, you don't really need to worry. You just take it into account. It's all there. And it's actually, it took much longer to state the problem than to actually calculate this. Very easy. That's typical of the use of energy. That's one of the reasons we like energy conservation. Yes, Eric.
So, I was a little concerned when I did this problem. The potential energy from the spring was caused by compressing at 30 centimeters. And once it's released, it doesn't account for that extra 10 centimeters when the system was originally at rest.
Okay, wait, I'm not following here. So it's released from rest here.
Right, well, so at rest...
The spring's going to push this thing. The spring is an ideal spring. It has no inertia. Maybe that's the problem here. We're neglecting its inertia. The spring is assumed to be very light compared to the mass.
Okay, so it still would be pushing on the mass even though it's past that 30 centimeter mark.
Okay, yeah.
It was originally at rest.
So it's going to push. This thing's going to rise. It's going to accelerate. Okay. Once the mass gets here, the spring comes to rest instantaneously. And you're thinking, that's not right. But that's because you're thinking realistically, and your spring has inertia. The spring has negligible inertia. So in practice, if this is much lighter than the mass, the spring will, but it does have some mass, the spring will actually go farther and it'll ring down here. And eventually, due to internal friction, it'll damp out, right? But we're neglecting that because its mass is very small. But we are going to lose some energy into that spring. Due to its motion, it will actually ring down there. Is that getting at your point?
Sort of. It was, well, I was thinking once it passed that 30 centimeter mark where it was initially compressed and the whole thing was at rest.
Okay, wait. First of all, this is the... I'm confused
So
here.
starting out...
This is the unstretched state. So when you say 30, do you mean 40?
I meant the 30 centimeters it took to push down the spring with the mass. Since the whole thing was initially balanced at 10 centimeters,
Right.
the spring expanded past that point to where...
The spring's still exerting an upward force.
Okay, that's why it was still considered
It's less than the force of gravity, but the spring is still exerting an upward force at this point.
Okay.
And then it goes to zero there, when the spring becomes unstretched.
Okay.
Yeah. The acceleration's not simple here. You want to do this from a Newtonian point of view? You can. It's not, first of all, because a spring is involved, it's not constant acceleration. You'd have to integrate the equation of motion, but you could do it. It's much easier to use energy conservation. If you cared about the details of what's going on here, then you'd have to go in. You're going to essentially be using Newton's second law. I mean, you can get some information from energy, but you're going to have to differentiate, and you're going to find, of course, that the acceleration is not constant here because we've got a spring, not constant force. Any other questions? Okay, this is a classic. Some of you might well, I doubt it. But this is a genuine classic. You have, and everyone states it differently. You can look at the way they state it. But here's the idea. We have this like hemispherical hill here, okay? Or semicircular. This is some kind of curved ramp here. And it's an arc, it's a semicircle, okay? And it's frictionless, and there's a mass that's released from rest at the top, or it's given a very slight amount of velocity. This is an unstable equilibrium point, right? It's like an inverted pendulum. similar to an inverted pendulum. And so if you release it from rest very precisely at the top and there's no vibrations, okay, classically it will stay there. But you know, in practice, it's just the slightest fluctuation, this thing's going to take off. It's unstable equilibrium, like we talked about yesterday. So that's what we're going to imagine here, that this thing is going to start to go down here, but it starts with essentially zero kinetic energy, essentially zero velocity. But technically speaking, it has to have a very slight velocity, or otherwise it'll just stay there forever. But we're going to assume it's very small. And this is a typical case for unstable equilibrium. It just takes a slight fluctuation and it's gone. Okay? So we want to find the angle at which the mass departs from the hemisphere here, from this. That's the problem. And you're probably reacting the same way. I think the first time I saw this, I think I was a undergraduate freshman. I don't know, back then we might have had it in high school. Things were different back then. You know, the Cold War was just raging on, so. And it wasn't clear that we were in first place. In fact, we weren't, right? Because the Russians sent up the first spacecraft, right? Yeah, that had a huge impact in this country. It was so huge that people said, look, we're doing something wrong. What are we doing wrong? Well, our children aren't being educated enough. So they dumped huge amounts of energy in education. That's just one part of the Cold War that you may not know about. So I'm a product of the Cold War. We did serious physics in high school, okay? Because a lot of people felt that the survival of the country depended upon it, right? So you know, you got nuclear weapons, you can put them into space. Let's see, is that going to cause us trouble? Right, you figure it out, right? And then submarines too, right? So I probably did this in high school. So when I was in elementary school, here's another story. I just remember when I was in elementary school, the Stanford, I grew up in the Bay Area, not far from Stanford. There was, all this money was being put into education. And one of the things was to develop mathematics. So there was SMSG, the School Mathematics Study Group out of Stanford. They decided that children could learn set theory. Children should know how to prove that the square root of 2 is irrational. I'm not kidding you. Okay, so when I was in elementary school, they used our school with one of the test sites. So we stayed a little bit after, like an hour after school, or I don't know, 45 minutes, and we took these tests. You know, they wanted to see if their material. We were using the material during the day. They wanted to give us their own tests. They're not going to trust the elementary school teachers, right? Yeah, of course not. Okay, so they gave us these tests to see how well how well we knew how to prove, you know, that the square root of 2 is an irrational number in elementary school. Yeah, I think they went a little bit overboard. Okay, and they would pay us $2, and they were always 2 crisp new dollar bills. I distinctly remember that. That sounds like a joke, right? But this was the way it was. You know, this was the days of duck and cover. You've seen the, yeah. Oh yeah. We practiced that. Okay, sorry now.
So how to do?
Well, I don't know. I mean, all I know is that when we would take national tests, this is up in what later became Silicon Valley, known as Silicon Valley, okay? That's where I grew up. We would take these national mathematics tests, and we would all be in like the 99th percentile for the country. And we're thinking, see, what does that mean? You know, what's going on in like Nebraska or somewhere like, is anybody from Nebraska? Sorry. So, I think first of all, our parents were in the aerospace industry or something like that. So that but yeah, I'm a product, and I'm not the only one who's I was strongly influenced by the Cold War. So I don't know why I started talking about that. Oh yeah, so I might have seen this in high school, okay? But it looks like a hard problem, and it's not easy, as you can tell. So how do we solve this? Well, we know energy is conserved, but that alone is not going to give you the answer here. It's obvious. We got to, what specifies, there's this particular angle here where this thing departs. How do we specify that? What's going on? Think normal force. Just as it's about to depart, or just as it departs, what's the normal force goes to 0. So here, when it's in contact, we have a normal force, right? And we can write down, looking in this direction, we can write down that the net force is the mass. We know there's going to be a net centripetal, there has to be a net centripetal force here. And it's going to be this component of gravity minus the normal force. And that will be the mass times the acceleration. So it's mv squared over r for circular motion here. Now there's going to be some tangential acceleration, but we don't need to worry about that. We're just looking, what we want to do is get in the information that what this theta is. It's where the normal force just goes to 0. So we're going to set n equal to 0. Now we get this relationship. Okay? And this is, you know, if you put a 1/2 here, that's the kinetic energy at the point where it departs. Okay, now we use energy conservation. The initial energy will equal the final energy. I'm going to choose my reference to be here. You can choose it to be anywhere. Doesn't matter. We did an example. We redid a problem in lecture where we moved the reference level and, you know, went back to the starting point of the problem. We get the same answer, right? Has to be, assuming you don't make a mistake. So I'm going to choose this as my reference level. The initial energy is just mgr. It's all potential. The kinetic energy initially is 0. There's some very slight kinetic energy, but we neglect that. Our answer is valid in the limit of 0 initial kinetic energy. So the final energy, I'm going to call my final point just where it leaves, just where it departs. And there's going to be some potential energy. So this picture here, this represents where it's just about to leave and go into projectile motion. So the potential energy is mgy, this distance right here. Do you see this right triangle right here? I need to find this leg. So that's going to be r times the cosine of theta. And that's going to be my height. So down here, where are we? Here's the initial energy. It's all potential. The final potential energy is going to be mgr cosine theta, because that's this height right here, which is the same as here, is r times the cosine of theta. And then it has some kinetic energy. And oh, by the way, you might say, well, we don't know what that is. We don't, but we know it in terms of theta from our force diagram here. So at that point, the process is over. Okay, we're going to have one equation and one unknown. So I did this kind of I don't know if this, I think I could have done this better, but it doesn't matter. Once we get this information into here, we've got one equation and one unknown theta, and you can solve for theta, and it turns out to be the angle whose cosine is 2/3, which is approximately 48 degrees. Yeah, classic problem. Oh, they ask for the height at which it leaves. It's just r cos. That's not really important. Once we're done, once we find that angle. So that's an interesting problem. It's challenging. Anybody have any questions? Okay, so this is an example. This is one-dimensional motion. I know you're probably looking at this the same way I am. I see a bead of mass on this wire here. That's not really what's going on. This is one-dimensional motion, and this particle, this object here, is subject to different forces. Okay, there's external forces on it. And these are conservative forces because we're given the total potential energy. It's a function of position. So this is a plot of the potential energy as a function of position here. The particle's actually only moving one direction, but most people, when they look at this, they see this as like a bead of mass on a wire, and that you can get away with that, but you can hit It happened to me once. I made a mistake, and you don't want to take this too far, this idea of a bead of mass on a wire, and I warned you about that yesterday. Okay, so what we're given here is that initially it's between 0.4 and 5 here, or 4.5, and it's moving to the left at 7 meters per second. That's the initial condition. And we're asked here, we're given the mass, given the potential energy, so that means that it's just conservative forces. And we're given what these potential energies are here relative to some reference. So this is, in this section, the potential energy is constant, and it's 15 joules. Here it's changing linearly with position, and it goes up to 35 here. And the first question, I think, is, does it make it? Does the particle make it to this region? This force is going against the object. Okay? This is a positive force. Because you remember, how do we get the force from the potential energy? It's minus the derivative with respect to x. And I think we're going to do that somewhere in this problem. Yeah. So the derivative is negative. We have the minus sign. So this is a positive force. It's impeding the motion. Does the object make it into this region? Well, the easiest way to do that is to find its energy. Let's find the energy. The initial energy is kinetic. We're given that information, plus potential energy. It's 37 joules. Right? So I can put, the energy has to be constant here. I can put a line here at 37 joules. That's the energy of the particle. And now you tell me, does it make it to this region? Yeah, it's going to have some of that leftover kinetic energy. In fact, we can find the velocity. That leftover kinetic energy will tell us what the velocity is. And here it is. It's 2.1 meters per second. B and C has to do with what we just talked about. This is, so this is one of these cases where we're given the potential energy and we want to find the force. We know that it's a straight line here. So the force is going to be constant, and it's minus du dx, as we discussed yesterday. And sure enough, it's positive. The minus signs cancel here. That's the force. Okay. Any questions about that one? So the final one here is 53. And the idea is we've got this frictionless curved ramp here. We have some initial velocity here. And, well, we assume it remains in contact with the ramp here. And then here, there's a rough spot. And the problem is to find the distance the mass is going to move along the rough spot. Eventually, it's going to come to rest. We want to know that distance from the initial point here. And we're given some coefficient of kinetic friction. So this is an example of where we want to use mechanical energy is not conserved. Now it is conserved here. Mechanical energy is conserved here. And most students will split this problem into two parts. They'll find the they'll find the velocity here using energy conservation. And then once you know the initial velocity, you know the friction. That was the first friction problem we did, probably. I remember this now. Which it's a natural first problem to do. Once you've learned about friction, in particular kinetic friction, then you can solve the age-old problem of, how long it takes a block to come to rest, given some initial velocity. So that's naturally how students do it. But we're going to do this from an overall. This is going to be our initial point. That's going to be our final point. And we just have to respect now the fact that the mechanical energy is not conserved, but it has to be identical to the work done by the non-conservative force, which is the friction force here. So I invite you to do it in two parts, but you don't have to. And this is more direct and it's easier. So, what's the final energy? What's the final mechanical energy? I'm going to call this my. Wait a minute, I'm going to call this my reference level for gravitational potential energy. So what's the final mechanical energy?
Some
mgh. Hey, all you got to do is look at it. I know it's you have to think a little bit here. You know, so I see this thing sitting here. The motion's over, right? It's got, according to my reference, it's got mgh of potential energy, right? So I have to respect that. Initially, what potential energy does it have? Zero. Now, if you can set your level up here, and then it will have some initial negative. You know, you can do it. You're going to get the same answer if you do it right. But anyway, so final energy is all potential. Initial energy is all kinetic, according to my choice here. That has to be the work done by the conservative force. And we know what that is. This is a constant force against the motion. So the work done by friction is minus the coefficient of friction times the normal force, mg, times d, the distance. And that's what we're after. So this is it. This is one equation and one unknown. So it looks like I decided to do this algebraically. You can plug numbers in at this point if you want to. I decided to do, for whatever reason, I decided to do this algebraically. The advantage of that is you can then look at special cases here, which I didn't do. But we have one equation, one unknown. We can easily solve for d, and you get a number, 1.2 meters. Okay, does anybody have any questions?